Imagine astronomers discovering a galaxy that seems to have almost completely lost the invisible material believed to hold galaxies together. At first, that might sound like just another strange object in the night sky. But the deeper scientists looked, the more unusual the story became. This wasn't simply an isolated galaxy with an unusual composition. It appeared to belong to a small group of remarkably similar galaxies located in the same region of space. And that raises a much bigger question. If dark matter is such a fundamental part of how galaxies form and survive, how can a galaxy exist with almost none of it? To understand why this matters, we first have to understand the mystery of dark matter itself. When astronomers look at a galaxy, they aren't seeing everything that contributes to its gravity. Stars, planets, gas, and dust produce light that telescopes can detect. But the motions of stars and galaxies reveal the presence of something much larger that cannot be seen directly. This invisible substance is what scientists call dark matter. The evidence for it goes back decades. One of the most important breakthroughs came from astronomer Vera Rubin, whose observations of spiral galaxies revealed something that shouldn't have been happening if visible matter was all there was. Stars far from the centers of galaxies were moving much faster than expected. Under ordinary gravitational physics, the outer regions should have been moving more slowly. Yet they remained in stable orbits at remarkable speeds. It was as if an enormous amount of invisible mass surrounded the galaxy and supplied additional gravity. Rubin's observations became one of the strongest pieces of evidence that dark matter wasn't simply a mathematical idea. Something unseen appeared to be shaping the universe. Today, astronomers estimate that dark matter accounts for roughly a quarter of the universe's total energy budget, while ordinary matter, the material making up stars, planets, people, and everything we can directly observe, accounts for only a small fraction. And here's the strange part. Despite decades of experiments, scientists still don't know exactly what dark matter is. They can observe its gravitational influence. They can map its distribution. They can watch it bend light through gravitational lensing. But the actual substance remains invisible. That is why a galaxy apparently containing almost none of it is so interesting. It could provide scientists with something extremely valuable, a natural laboratory where ordinary matter and dark matter appear to have been separated. One of the most fascinating examples is an ultra-diffuse galaxy known as DF9. Located roughly 65 million light-years away in the region surrounding the galaxy NGC 1052, DF9 is extraordinarily faint and spread out. It contains relatively few stars for its physical size, making it difficult to detect and even harder to study. Objects like this are known as ultra-diffuse galaxies. They can be surprisingly large while containing only a tiny fraction of the stars found in more familiar galaxies. And DF9 wasn't even recognized as a galaxy immediately. Its faint appearance initially made its true nature difficult to determine. Only after researchers examined the object more carefully did they realize they were looking at something much more unusual. What made DF9 particularly interesting was its location. Nearby were two other galaxies, DF2 and DF4, which had already attracted enormous attention because measurements suggested they contained remarkably little dark matter. Finding one galaxy with an unusually low dark matter content could potentially be explained by measurement uncertainties. Finding two was considerably harder to dismiss. Then researchers began looking at the surrounding region more closely. They discovered that several faint galaxies appeared to form an unusual linear arrangement. Instead of being scattered randomly across the sky, these objects seemed to trace a narrow structure. That immediately suggested something important. Perhaps these galaxies weren't independent systems that happened to end up close together. Perhaps they were created by the same extraordinary event. If that idea was correct, then other galaxies along the same structure should display similar properties. And that made DF9 an especially interesting target. The next challenge was figuring out how much mass the galaxy actually contained. Astronomers have a powerful method for doing this. They measure the speeds of stars. The faster stars move within a galaxy, the stronger the gravitational field must be holding them in place. If a galaxy contains a large invisible dark matter halo, its stars should generally move faster than they would if only the visible material were contributing to the galaxy's gravity. So instead of searching for unusually fast stars, researchers studying DF9 were looking for something almost the opposite. They wanted to know whether the stars were moving unusually slowly. To make that measurement, researchers used an advanced spectrographic instrument capable of analyzing extremely faint astronomical objects. DF9 is so dim that collecting enough light wasn't easy. The observations required many hours of exposure across multiple nights. But eventually, the researchers obtained enough information from the galaxy's faint stellar light to measure the motion of its stars. And the result was striking. The measured velocity dispersion was only around 6.5 kilometers per second. That number becomes much more meaningful when compared with theoretical expectations. A galaxy of DF9's size and visible mass would normally be expected to show significantly faster stellar motions if it possessed a conventional dark matter halo. Instead, the measured value was dramatically lower. The simplest interpretation was that DF9 contains very little dark matter compared with an ordinary galaxy of similar size. Its estimated total mass appeared to be much closer to the amount of ordinary matter that astronomers could actually see. That made DF9 more than just another unusual galaxy. It became another piece of evidence in a growing puzzle. Because now there weren't simply one or two strange galaxies. There appeared to be a group. And their arrangement suggested that something violent may have happened in the distant past. One possible explanation involves a collision between galaxies. When galaxies collide, their stars, gas, and dark matter don't necessarily behave in the same way. Stars are mostly separated by enormous distances, so they can pass through the collision without directly hitting one another. Gas is different. It can collide, compress, heat up, and lose energy. Dark matter is different again. If dark matter interacts extremely weakly with itself and ordinary matter, it can pass through a collision almost like an invisible cloud. That difference in behavior creates an intriguing possibility. During a high-speed galactic collision, ordinary matter could become concentrated in one region while much of the dark matter continues moving onward. Eventually, the remaining gas and ordinary matter could collapse into new structures. The result could be a galaxy containing far less dark matter than expected. This idea is related to observations of much larger colliding galaxy clusters, where astronomers have seen evidence that hot gas and dark matter can become spatially separated. If a similar process occurred on a much smaller scale, it could potentially explain why DF2, DF4, and DF9 appeared to be unusually deficient in dark matter. And that is where the story becomes especially interesting. Finding a galaxy without dark matter doesn't necessarily undermine the dark matter model. It could actually support it. Why? Because if dark matter can be physically separated from ordinary matter during a violent event, then observing a galaxy where the two components have been separated is exactly the kind of evidence scientists would want. Instead of merely saying dark matter exists because galaxies appear to need extra gravity, astronomers could begin studying what happens when that invisible component is removed from a galaxy. That turns the absence of dark matter into an experiment written across the universe. And there is another reason DF9 matters. Its discovery wasn't simply a random surprise. Researchers had a specific prediction. If the galaxies in this unusual linear structure were created by the same violent process, then other galaxies along the structure should potentially show similar characteristics. DF9 became a test of that prediction. And when its stellar motions were measured, the results were consistent with the idea that it too contains very little dark matter. That makes the discovery much more significant than an isolated anomaly. It suggests that the universe may have natural environments where ordinary matter and dark matter can be separated on enormous scales. But scientists aren't stopping with 3 galaxies. There are other faint objects in the same region that still need to be studied. If additional galaxies along the structure show the same unusual properties, the evidence for a common origin would become even stronger. And this is where the Vera Rubin Observatory could become extremely important. The observatory is designed to repeatedly survey enormous portions of the sky with extraordinary sensitivity. Its wide-field camera will allow astronomers to discover huge numbers of faint and previously overlooked objects. Among them could be many more ultra-diffuse galaxies. Some may contain ordinary amounts of dark matter. Others could turn out to be remarkably deficient. And perhaps some will reveal entirely new structures that scientists haven't even imagined yet. The irony is remarkable.